Hello everyone, my name is Kaushal Karpram and today I'm going to be solving a math problem with you guys. This math problem is from the 2019 AIME I. This contest took place a couple of weeks ago, March 13th to be exact. And this is question 12, and this is a 15 question contest, so number 12 is one of the harder ones. Okay, so the problem asks, given that f of z is equal to z squared minus 19z, there are complex numbers z such that z, f of z z are the vertices of a right triangle in the complex plane with the right angle at f of z. There are positive integers m and n such that one such value is m plus the square root of n plus 11I. Find m plus n. Okay, so just a quick introduction on complex numbers. They're numbers that can be expressed as a plus bi. I has a definition such that I squared is equal to -1. For most people will know that there's no real defined value for something that is the square root of -1. So that's why we have defined I to be that value. I is an imaginary number. So now we have complex numbers a plus bi. So now I'm going to talk about the complex plane. A complex plane is a way of drawing complex numbers. We say that there's a real component and an imaginary component. The real component can have any value, but it needs to have a legitimate decimal notation. It could be pi, like 3.1415, so on. And the bi is the imaginary part because, just like we said, there is no real value such that a number squared is -1. So the complex plane is a way of drawing complex numbers. So if we say we want to draw the complex number 2 plus 3i, we would go 2 to the left and 3 up. And we say that number is 2 plus 3i. So a bit more about complex numbers. If you have a number a plus bi, the magnitude is defined to be as a squared plus b squared. Just think about it in terms of the Pythagorean theorem. This length is the square root of a squared plus b squared. And another way that we can represent complex numbers is by using trigonometrical notations. So say we have the complex number a plus bi again. We said the magnitude is the square root of a squared plus b squared. We can also define this to be the radius, r. And one way that we can express complex numbers is r cis theta, which translates to r cosine of theta plus r I sine theta. You should know, so again, you see here that this is the real part and this is the imaginary part. Similar to this. So how can we express a plus bi in this form? We know that the radius is a squared plus b squared, so we say root a squared, b squared, cis theta. But we don't know what the theta is, and I'm not going to bother trying to explain how we find it, because it should be basic trigonometry. And so if we define this to be theta, b, a, we say tan of theta b over a. So theta is the inverse tan of b over a. Pretty simple. So now let's try playing around with the numbers that they gave us. So let's just find the 3 points. Z, f of z, and f of z. And one thing the problem said is there's a right angle at f of z. Okay. So we know that this has to make a right angle with this. So we call this complex number. So we can add and subtract complex numbers just like we can do with any numbers. And we can give them their own radiuses and magnitudes. And just FYI, so when you want to multiply complex numbers, say one of them is R1 CIS theta 1 and one of them is R2 CIS theta 2. Their product is defined to be R1 R2 CIS theta 1 plus theta 2. Likewise, if you divide them, you can get R1 or R2 CIS theta 1 minus theta 2. So, what this is saying here is that they make a right angle. So, if we just draw another complex plane and say let's call this complex number here z minus f of z, and call this complex number here f of z minus f of z. And we know they make a right angle with each other. What does this mean exactly? Well, we can think back in terms of this. So what we say is, when you divide these two, we can say that the complex what you get is a complex number, some r, CIS of 90. Why is it 90? Because what we said here is when we multiply complex numbers together, we just add the angles that they make with the real axis, and we know that they make a 90-degree angle with each other. So what's special about this is we open it up. R cosine of 90 plus Ri sine of 90. Cosine of 90 is 0, so that cancels, and what you're left with is Ri times sine 90. You know that sine 90 is 1. So the critical epiphany here is that the ratio of these complex numbers is purely imaginary. It does not have a real component. So now that we know this, let's play around with some of the algebra. So the numerator is z minus f of z, and the denominator is f of z minus f of z. So we know z minus 19z minus, no, it's plus 19z minus z squared. And for f of z, we're not going to really plug and chug it out completely. We're going to make this slightly easier on this and just define it to be f of z squared minus 19z, that into z squared minus 19z minus 19. Because think about it, we're just inputting this into the greater function over there. Minus z squared minus 19z. So let's simplify. Okay, what you see here is a quadratic, but we can factor this out too. And let's try to factor each and every single one down to its prime factors. Okay, I realize that you might not be able to see it, so I'll just move it up. I'm just going to write some of this. So let's try to factor out whatever we can from both the denominator and the numerator. So what can we do? We can cancel out this, both z minus 20 factors, and cancel out both z factors. So what we're left with is negative 1 over z squared plus minus 18z minus 19. Okay, so this is the ratio between those two complex numbers, and what we know is their ratio should be purely imaginary. So what we're gonna, and we don't know what r is here. Think about it as the plus c when you calculate an integral. It could really be anything. But what we're gonna work off here is we're not gonna try to calculate r. We're gonna try to work off the fact that it has 0 real component. That's gonna be what we're gonna work off of. So what we're gonna do is we're just gonna take we're just gonna divide both sides by negative 1. And we're going to take the reciprocal of it. Okay, so this was just a quick mental calculation that I did to calculate what the reciprocal of that is. And if you can verify it by just quickly multiplying those out, and you'll see that they multiply out to 1. So what we have here is z squared minus 18z minus 19 has 0 real component, again. So how do we move forward? Do we try to calculate a root of it? Not really. We know that we need to find something in this form, and that's what we can work off of. So let's say that this is 0 plus I r. Okay, well, let's think about it. Let's just think about what the contributions that are made to the real part of it. Forget completely about the imaginary part. Again, I'm omitting the imaginary part because what we're really trying to focus on is the fact that the real part of this is 0, so we just move this 19 over, and we're saying that z squared minus 18z is equal to 19. So let's set up some new variables. Let's say that z is equal to a plus 11I, and take critical note of what a is here. A represent m plus the square root of n, because think about it, that's what we're trying to find out. So z is equal to a plus 11I. So we say okay. Again, remember how we didn't completely calculate the real component, the imaginary component? We're going to follow that same logic right here. We're just going to care about what is the real part of it. So let's just try to factor it out. Let's just try to factor out whatever realness we can get out of it. So a into a minus 18, a squared minus 18. That's the real part that we can get from the real numbers that are multiplied together. And actually, I misstated that. We don't know that a is real per se, but yeah. And then 11i times 11i. That's negative 121. is equal to 19. So notice how I didn't multiply 11i times a, or 11i times a or 18. Why didn't I do that? Because, again, we are completely omitting the real value. No, we're completely omitting in this calculation, we're basing our logic off the fact that we know that the real value of the ratio is 0, and we know that there is some value for the imaginary part of that ratio, but we don't care what it is. So we know that a actually is real because, think about it, a is equal to n plus root n, and by the definition of the problem, they are integers. So it's not, they have no imaginary part of it, and we know that they're real. Sorry for the confusing statements that I made before. So a squared minus 18 minus 121 is equal to 19. I'm going to move that up here. A squared minus 18 minus 130. No, sorry, 140 is equal to 0. So we can solve this using quadratic formula. Negative 18 minus square root of b squared minus 4ac over 2a. And this is actually plus 18, sorry about that, because negative or negative is positive. So we get is so 884. So what we get here is, we know that we can factor out a factor of 2 from that square root, and seeing there's a 2 at the bottom, we do just that. We get that the real part of this m plus n plus 11i is 9 plus or minus the square root of 221. But we're only interested in the value that follows this form, given that n is a positive integer. So we only have to consider 9 plus the square root of 221. That's m plus root n. So m plus n is equal to 9 plus 221, and that is a final answer of 230. So that's how you do this problem. Again, I'm just going to summarize how we did this problem real quick. We worked off the fact that they make that when you subtract the complex numbers, they make a ratio that is purely imaginary and has no real component. And that's how we based our algebra off of. And when we factored, we saw that we factored, and then what we saw was we can take advantage of the fact that there's no real component, and we can set, and if you only consider the real products that you get when you multiply, and what we also did was we set up new variables saying that z is equal to a plus 11i, and we knew that a was going to be purely real. Why do we know that? Because of this statement. They gave us the value of the real part of this of the imaginary part of this ratio, and that's what we worked off of. We plugged that in, and what we did is we completely ignored the imaginary parts on this side of the equation and on that side, because we already knew that they were going to eventually cancel, so we just considered the real parts. We worked it out, and then this is what we got for m plus the square root of n by solving this quadratic equation here, and this is our final answer. Appreciate your time and listening to me. Thank you.